Hello, welcome to this next video in which we're going to continue on our quest to solve linear ordinary differential equations with variable coefficients. So equations like this on the board, where we've got t d squared y by dt squared plus dy by dt plus ty equals 0. And of course this is a capital Y in both of these equations for a very good reason, and that's because we're actually going to use Laplace transforms to solve this equation and equations like it. So in previous videos I have solved equations similar to this, for example when there was a variable coefficient in front of the y but not in front of the y double prime or the y. So where there was a coefficient there in front of the y prime but not here or here. Now in those videos I actually specified what a linearly independent solution was, so that we could see if it solved this equation on the left and equated it to 0, and then proceed from there to find the general solution. That once you've got a linearly independent solution, it's generally very easy then to find the general solution. What we're going to do in this case is use Laplace transforms, because we don't then need to guess a solution and try and work out what solves this left hand side. It takes, using Laplace transforms actually takes us through and finds that initial linearly independent solution. So what we're going to do is we're going to take Laplace transforms at both sides of equation 2. So we've got Laplace transform of t times capital Y prime prime, and in fact you would normally initially write it like that. We'll call that equation 3, if I can actually write it with a steady enough hand. I do seem to have a problem writing a lot of the time. Okay, so that's equation 3. Now this, because of its linearity, can be written in this form. The Laplace transform of t capital Y prime prime plus the Laplace transform of y prime plus the Laplace transform of t capital Y, and that's going to be equal to 0 on that side, because the Laplace transform of 0 is just 0. So we'll call that equation 4. Make that look more like a 0. There we are. Right, now before I go any further I should have specified initial conditions, because we need to know that capital Y of 0, that is the value of y when t is 0, is equal to a constant c1, and the derivative of y with respect to t when t is 0 is just equal to a constant 2. So y of 0 is c1 and y prime of 0 is c2. As usual, I've taken the cart before the horse. I should have specified these initial conditions to begin with, and I've forgotten as usual, so it kind of interrupts my flow. But there we are, that's me, the blundering mathematician, and believe you me, I blunder. So I hope you can follow what I'm doing. Now, it turns out that when we take the Laplacian of, and I'll outline this in red. When we take the Laplacian of that, we get a negative derivative of the Laplace transform of y double prime. So we get minus d by ds of because as you can see, there's a coefficient of t there. That's what makes all the difference. So we've got minus d by ds of s squared lowercase y, and we've also got let me just see, I've made a mistake there. Right, so we've got minus s y of 0 there, minus y prime of 0. So all of that derivative of what's inside the bracket is this term here underlined in red. And then we've got a Laplacian of, or a Laplace transform of y prime, which is plus sy minus big Y of 0, so it's capital Y of 0, minus the Laplace transform of this, which is just dy by ds, and that's equal to 0. So basically, you take the Laplacian of the left-hand side, you can rewrite it as that, and then everything comes out in that form as so. Now, we know that y of 0 is equal to c1, and y prime of 0 is equal to c2. So we've got minus d by ds of s squared y minus c1s there, minus c2, plus, and I don't think I'll be able to write it on here, but we'll try, sy minus c1, right? And then we've got our minus dy by ds there, and that's equal to 0. Now all we have to do is differentiate this part on the left hand side to start simplifying the formula. So what we've got is, if we take the derivative of s squared y, we get minus 2ys minus s squared dy by ds plus c1, because the derivative with respect to s of c1s is just c1 constant, and the derivative of that constant there is just 0. So we've got a plus, or is it a minus 0? It doesn't really make any difference. And then we've got plus sy minus a constant, which is c1, minus dy by ds equal to 0. So there you can see we've got a more simplified version of this now. We've actually got a linear ordinary differential equation, which will be easy to solve when we've simplified it. So what you will notice is that the constants just cancel, and this has the same form as that. So we've got minus 2ys plus sy. Well, sy is just ys. So minus 2ys plus ys is just minus ys. So if we collect the terms together, so let me get a different colour. If we collect these terms highlighted in green together, then what we get is minus s squared dy by ds minus dy by ds. And then adding the minus 2ys and the sy, we get minus ys, and that's equal to 0. Now, I'm going to simplify that a little bit further because we can factor out the dy by ds's. But before we do that, we'll multiply through by 1 so that we get the following. Right, so I've multiplied through by minus 1 to get this, and then we've got s squared plus 1 times dy by ds plus ys equals 0. Now actually I'm going to skip a step, but I'll explain what I'm doing. Basically I'm going to put this ys term on the other side so that it becomes minus ys. Now then, dividing, if we divide both sides of this equation by s squared plus 1 and divide both sides by y and then multiply both sides by ds, we get the following equation. So we get dy over, there's a bit of a long derivative, isn't it? Let's just write that a little bit more convincingly. So we get dy over y equal to minus s over s squared plus 1. We'll put that in brackets. ds. And of course, when you have something like that, you must put in integral signs. Now, hopefully, if you are familiar with high school mathematics, like A-level mathematics and a bit of calculus, you'll know how to solve these integrals. The left-hand side is very easy because it's basically 1 over y dy, which integrates to give log of lowercase y. And that's equal to, well, the derivative in the numerator is 2s. So it's minus 1 over 2s, which actually cancels with this s in the, did I say that was a numerator on the bottom? That's the denominator. So this s cancels with the s in the numerator on the top part of the fraction. And that's equal to log s squared plus 1. So basically, we've got the log of y is equal to, and there should be a minus sign in there, good, we've got that, minus a half log s squared plus 1. Right, we're not quite done, but we're getting close towards certainly over halfway. Now, if I just erase this from the board, right, we've got the log of y equal to minus a half log of s squared plus 1. Well, this can be written as the log of y is equal to the log of s squared plus 1 to the power minus a half. And by the way, I forgot to do something. That should have a constant of integration. Always forgetting these things. As I told you, I'm a blundering mathematician, and that's what I should change my name to, I think, given the amount of blunders that I make. So we'll call this, for the sake of convenience, log of c. So we've got the log of c here. That's just a constant, you see, but I've chosen it to be a logarithm because it's more convenient that way. You might just call it C, but it doesn't really matter because everything would fall out correctly in the end anyway. If you take anti-logarithms of both sides, so if you raise everything on both sides to well, if you take the exponential of both sides, you get y equals e to the log of s squared plus 1 to the minus a half plus log of c. Now, this becomes y equals, well, if you remember, in previous videos, I've explained that if you have the exponential of a logarithm, like 5, so the exponential of a logarithm of 5, then all what that comes out to be is simply 5. If you have the exponential of a logarithm to 1400, then the answer is just 1400. So the exponential to the power of a logarithm of, say, x is just x. So in this case, the exponential of this logarithm is just s squared plus 1 to the power minus a half. But we've also, in fact, actually, I've skipped a step because we can write this. We can write this like this. So going back to what I said, this term here just becomes s squared plus 1 to the power minus a half, and this term here just becomes c, right? So I hope that's not too much of a blunder. This can be written as c over s squared plus 1 to the power of a half, which is the same as writing c over s squared plus 1, right? Now, that's what y is equal to. What we now have to do is find out what capital Y is. So capital Y is the solution to the original equation, or at least one of the solutions. So if you remember, if you take inverse Laplace transforms of this lowercase y, you get back to y. But what you do on the left-hand side, you must do on the right-hand side as well. Right? So, let me clear the board over here. Right? So we've got this. We need to find what the inverse Laplace transform of c over the square root of s squared plus 1 actually is. Now, there is, as I can see, there's no real easy way of doing this except using the Laplace integral formula for working out what the solution is, and you probably get a series or something like that. But anyway, the inverse Laplace transform of that expression, c over the square root of s squared plus 1, is quite simply equal to c1 times j naught of t. Well, what's that? If that's a solution to that, what is that? Well, it's a Bessel function because this is a Bessel equation. And in fact, this is often written, I'll just write it here and then rub it off the board. That is often written as t squared y double prime plus ty prime plus t squared y equal to 0. But as you can see, you can cancel the t's. So that is a Bessel ordinary differential equation, and that is a Bessel function. That solves that equation, and therefore solves equations 1 and 2 as well. Now, that is not the only solution. So what we're going to do is we're going to use an integral formula. And you might remember this from previous videos where I said the integral formula for the second linearly independent solution, y2, is equal to, well, we'll call this y1. So it's equal to y1 times the integral of e to the minus the integral of p dt over y1 squared dt. And I have to remember that's time we're dealing with here, because this is all in terms of time. Previously that was dx, but that's because or previously these terms here were dx's, because the original equation was in terms of x's. But it doesn't really matter. You just adapt it to whatever you to whatever you have, to whatever the question is. So first of all, we need to rewrite equation 1 to work out what p is. So if we rewrite equation 1 as, or we could rewrite equation 2, it doesn't matter. So we've got d squared y by dt squared plus 1 over t dy by dt plus y equals 0. Then it turns out, as you might recall from my previous videos, that p is equal to this term here, 1 over t. Right? So p is equal to plus 1 over t. If that had been negative, you would have included that as well. But it's a plus 1 over t. So our integral formula becomes y2 equal to y1. Well, we know that y1 is c1 j sub 0 of t. So we've got c1 j sub 0, well, we'll just ignore the t for now, times the integral of e to the minus the integral of 1 over t dt over c1 squared times j naught squared. Can you see we've squared the first linearly independent solution so that we get c squared j naught squared? And if we simplify that, we get, well, we can take the c1 squared outside the integral because that's just a constant, so that we get j naught over c1, and that is multiplied by the integral e to the minus log of t, and there should be a dt in there as well, over j naught squared. So y sub 2 is equal to j naught over c1 times the integral of e to the, well, let's just write it over here where there's a little bit more space. So that's equal to j naught over c1 times the integral for e to the log t to the minus 1 over j naught squared dt. And so this comes out to be equal to e to the power log of t to the minus 1 is just t to the minus 1 over j naught squared dt. Right? Now, you can try and simplify that as much as you like. You could rewrite this as j naught over c1 times the integral of 1 over t j naught squared. But unless you start using further complex or complicated mathematics, you won't find it very easy to do that integral. But you can actually work out what the integral is on a mathematical based computer like Python or Mathematica or MATLAB or something. So if you use mathematical software, that's what I was looking for. If you use mathematical software, you can work out what that integral is. And it turns out that y2 is equal to c2. In actual fact, I'll put that in afterwards. In actual fact, it's 1 over c1 y of 0. Now that is another Bessel function. But we'll rewrite that as y2 equals c2 y naught. This y naught is not the same as that y. They're completely different. That is just the representation of a Bessel function, that y sub 0. It just happens to look like this one here. So many apologies. So the general solution, actually that, again, what have I done? I've forgotten to include a constant of integration there. So that should have a constant of integration there. So if you multiply everything outside the integral sign by everything inside it, including the c, you get for your second linearly independent solution plus 1 over c1 j naught times another constant. So in actual fact this is c2 plus c3 j naught. Now we're nearly there. This is not the general solution. It actually is, but in a way, in a sense. But it's not really the general solution because we have to add it to that. So adding y1 and y2, we get the general solution y equals c1 j naught. I'll just write it as j sub 0 rather than j sub 0 of t plus c2 y sub 0 plus c3 j sub 0. Now it turns out, like I said before when we were doing a similar sort of problem, working out the second linearly independent solution and from there the general solution, you get two terms here but they get absorbed into one another. So if you add the C1J naught to C3J naught, you just get another function in terms of J naught, where A is equal to C1 plus C3, and of course you've got your other solution here, which I'll call By of 0. Now that is the general solution to those either form of the Bessel equation, which is that or that. And well, that is that for that question. So I hope that I haven't been too blundering, and that you've again found this useful and helpful in what you do, whatever you're doing. So I won't yap on any longer, but I'll bid you farewell for now, and just say, please do check out my other videos and keep a lookout for upcoming videos of mine, including this one and future ones. And cheerio for now. So bye.